Oh wait, sorry, you're real low. Say it again.
Did you pass or not pass?
Oh, it was. Yeah. Did you heal or not heal? Right. So success or failure, and then the other one was.
That's the only one that I saw.
We're looking at this example here.
Yeah.
So what else do you know about each person? So I know whether their surgery was a success or a failure. Another thing I know about them, anybody else?
The cast, 46 weeks or less than 6 weeks?
Yeah, the type of treatment. All right, so from each person we know what type of treatment they got for their foot and whether it succeeded or failed. Whether they were healed or not healed because of it. So we know two things. The two things we know about them are categories. That will put them into one of these 8 spots. Right? If it succeeded or failed, and then what type of treatment they got. So you all have seen contingency tables before. You saw them back in chapter 4. Right? This one with the puppies. Right? We know two things about each puppy: the type of lab they are, and whether they're male or female. If you recall, we did tests for independence. The test for independence is the exact same thing as homogeneity of proportions. Homogeneity means the same. So sameness of proportions. If the proportions are the same, they're independent. You folks remember that? Chapter 1? So for example, male and chocolate. What numbers here have to do with male or chocolate? Anyone? Give me one.
5.
5. Yep, the chocolate males. What's another one?
25.
Yep, the total males.
8.
Yep, the total chocolates and the grand total. So what we did back in chapter 4, if you recall, is we looked at that ratio. Is 5 over 8, compared that proportion to 25 over 40 to see if they're equal. These are equal, so that means they're independent. Make sense? Do you folks remember that one? Or compare the proportions. 5/8 to 25/40. If those proportions are the same, they're independent. In other words, they don't affect each other. Knowing that it's male does not affect whether or not it's chocolate, and knowing chocolate does not affect whether or not it's male. The odds of it being male. That was just for one specific answer. Now we're looking at the whole thing, the whole gender versus type of puppy all together. So we're going to be looking at 5 out of 8, 15 out of 24, 10 out of 16, 30 out of 48 to see if those are the same. So we'll take a look. Does 5/8 equal 15 over 24, equal 10 over 16, equal 30 over 48? Yes, they do. They're all 0.625. So that means that gender would be independent of type of puppy because their proportions are the same. I should probably fix that 10 so it's more legible. Okay? Now, in real life, these proportions might be the same, but in real life, you're going to get a little bit of variance. Right? Like the proportion of heads when I flip a coin should be what?
50-50.
Yeah, 50-50. Makes sense because there's two options, heads or tails. But in real life, if I flip a coin 10 times, am I always going to get exactly 5 heads? No, there's going to be a little bit of variance just due to randomness, right? So we're not going to get exactly perfect proportions all the time. What we're testing to see is, are the proportions reasonable enough, are they close enough that we think the proportions could be the same, or are they so totally crazy different that they couldn't possibly be the same? And that's what we're testing in this test. See if the proportions are close enough to be that they could be equal. In other words, they could be independent of each other or not. There are many similar things, like O is still our observed values, E is still our expected values, expected frequencies. But now we have two other things, R and C. R represents the number of rows we have. In other words, how many different options are there for that variable. C represents the number of columns we have. In other words, how many options are there for the other variable. Columns are like, you know, if a house has columns, right, then they go up like this. So columns are these guys that go like this. Rows go along this way. Let's get a reader. Sean, go ahead and read.
Test for independence slash homogeneity proportions. The chi-square independence test can be used to test the independence of two variables. The hypotheses are H0, there's no relationship between two variables. Homogeneity proportions, P1 equals P2 equals P3 equals P4. Independent, O sub I equals E sub I. H1 is there's a relationship between two variables. Homogeneity proportions, at least one differs. Dependent, O sub I does not equal E sub I. If the null hypothesis is rejected, there is some relationship between the variables.
Right, so pretty much your book is going to focus on the red ones. H0 is that they're independent. So the one variable is independent of the other variable. And then H1 would be that they're dependent, those two variables are dependent. And then, like I said, on the exams, you can always just use O sub I equals E sub I. But your homework is going to probably focus on the independent and dependent. Remember, independent means the proportions are equal. So that's your H0. You can also do it like this. H0 is also all your no's, right? H0 is always your equals and your no's. No difference, no correlation, no relationship. And if you're not, like I don't do relationships. No relationships for me. I'm very independent, right? So independence, same thing as no relationships. Good? So that's another way to kind of keep that and remember that. All right. So we're going to put our data into contingency tables, like you've seen. The catch is the degrees of freedom. Degrees of freedom are kind of weird. It's your number of rows minus 1, multiplied by the number of columns minus 1. So before it was the number of categories minus 1, but now you have two groups of categories. So it's the first group of categories minus 1, and the second group of categories minus 1, and then you multiply those two. This is the same, the formula. For every single square kind of in your matrix, get the observed value, subtract what you expected to get, square it, divide by what you expected, and then you add them all up. There's your degrees of freedom. But this, you should circle this, you need this. So it's in your notes towards the bottom of page 83. I highly recommend that you box this and star it, because you absolutely need to know how to use that and do that. The expected value. Again, you need to compute the expected values. How do you compute them? You take the row sum, multiply by the column sum, and divide by the grand total. I'm going to show you what that means in just a minute. That's the formula. So again, you will need to find the expected value. I'm going to make you find this by hand, the first and last one at least. But then for the chi-squared itself, you can just do chi-square test of your observed. Does everyone see the square brackets here? They're little square brackets. When you have square brackets like that, that means matrix. So that's matrix A, which means that you're going to take your observed values, you're going to put them into matrix A. And I'll show you how to do that in a little bit. And then matrix B, that you put nothing into matrix B. Did everyone hear me? Do not put anything into matrix B. The formula will compute your expected values and it will store them into matrix B. So this is the chi-square test will output your expected values into matrix B. It'll overwrite whatever's in matrix B and put in, if this is a 2 by 7 matrix, it'll compute this expected value 2 by 7 matrix, and it'll overwrite B with that. So you put nothing into B. You will put something into A. Don't worry about B. It's just telling you where you're telling it where you want it to store the expected values. You could put matrix Q, and then it would store it into matrix Q. Right? You're just saying where it goes. It also gives you the chi-squared and the p-value. All right. So how do you compute? So here's an example. We'll go over computing these in just a second. So we are top of page 84. Get a reader. Jason, go ahead and read.
A researcher wishes to see if there's a relationship between the hospital and the number of patients infection. A sample of 3 hospitals was selected, and the number of infections for a specific year has been reported. The data are shown next.
Great. Everybody find out what 2 things I know about every patient. What 2 questions do I know about each patient? So what 2 things do I know about every patient? You folks give me one thing.
They're in a hospital.
What hospital they're in. So I know what hospital they're in. That's these guys here. Those are my outcomes. Does that make sense? What's the second thing I know about them? Over there? Type of infection. How many types of infection are there?
3.
3. So this is a 3 by 3 matrix. I highly, highly, highly recommend that you all do this whenever you get a problem like this, so you can clearly denote to yourself what your data is. Keep it separate from your totals, because this is what you're going to input into your matrix. It tells you what size your matrix should be, what your values should be. It also is going to help you a lot when you compute your first and last expected values, because I'm going to ask you to compute the first one in your matrix, which is the upper right corner. I'm also going to ask you to compute the last. Where's the last one? The bottom left corner. And people last class were doing all sorts of random things because they hadn't marked off where their matrix was, so they'd grab this one or they'd grab that one, and it was just kind of a mess. So make your matrix, and we're going to compute the first and last expected values. So first expected value. So for 41, that first one, I need to figure out what it should be, what I expected it to be. What is its row total? Yep, 119. Is everyone kind of see that? Total of its rows. What's its column total?
246.
246. And what's its grand total?
582.
Right. So if it's going to be blank over 246 equals 19 over 582, I need to figure out what we expect that to be if those portions were equal. Does that sort of make sense for folks? So let me rephrase what I'm talking about. I would say that this over that equals 19 over 582. To simplify that, to figure out what this blank is, I'll just give it to you, it's easier, is I call the expected value of, what row is it?
1.
First row, does everyone agree with that? Which column is it?
1.
1 comma 1. So this is going to be the row total, 119, times the column total, 246, divided by the grand total, 582. You just have to compute what that is. So let's go ahead and do that. We'll go ahead and do that. That's fine. $119 times 246 divided by 582. 50.30. If I round correctly. That's what I expect this value to be. So let's talk a little bit about this subscript here, 1 comma 1. When I first learned how to do matrices, I learned that this is row, comma, column, R, comma, C. Back in those days, RC colon was really big, so I just remembered it by thinking of RC colon. RC. Just whatever you need to do, think of RC. It's R, then C. Apparently RC Cola is still around because a student of mine a couple years back brought me a can of RC Cola. So I still have the can. Unfortunately, I left it in the car and it exploded in the car. But I still have the empty can. So I'll bring that in. But it's RC, row then column. The last one. What's my row? What's the row for the last one? That's this spot here. Does everyone kind of follow? What row is it? The third row?
Oh, 3.
Yep, what column is it?
3.
3. So it's E33. And again, I'm going to take the row total and the column total. I'm going to multiply those. Doesn't matter which one you write down first, just those two multiplied by each other. Divided by the grand total. So if I do that, 200 times 384 divided by 582, 131.96. Okay, so then there's my first and last expected values. And then I'm going to put the stuff in my brackets into my calculator. So I need to put it into a matrix. So everyone go to your calculator. And you all see this, the fourth one down on the far left says matrix in blue. Yours might be yellow or some other color.
Matrix D.
Yeah, matrix. Matrix. D is a different color. D is the alphabet. So, you have the second key to get the matrix, because the second key should be the same color as matrix is in. So I'm going to hit second matrix, and then this comes up. Leave the names alone. Don't mess with the names. Go over to edit. Right, so don't mess with the names. Just go over to edit, and hit enter on A. Again, second, and then down to matrix, and then arrow over to edit. We want, this is a 1 by 1. Everyone see that? I don't want a 1 by 1. What do I want? 3 by 3. So your row first, 3 by column. And as soon as I hit 3, all of a sudden I have 3 rows. I'm going to hit 3 here and hit enter. All of a sudden I'm going to have 3 columns as well. Bam. And just input them. If I use my keypad, I can put in 41 and hit enter, it's going to jump to the next one. So it makes it really easy to input them. Once you input them, double check and make sure you put them in correctly, because it's really easy to mistype something here. So double check that. Does everyone have their matrix input? Okay, get it input. Matrix, you got it? All right, so now we have an input. We're going to go to stat test. And we're going to arrow up, because it's towards the bottom, just the plain old regular chi-square test. Chi-square test, observe A, expected B, calculate, bam. There's our chi-squared and our p-value. So my chi-squared. So let's look at what I did. So what we did was we did chi-squared test. And then put down brackets with an A inside so that I know you put in matrix A into there. Right, so this is how you show your work. And then your chi-squared was 30.70. And your p-value was 3.53. 353%? That seems wrong.
E negative 6.
E negative 6. Anytime you're in a number, this is a number bigger than 1, you better have an E negative at the end. So E negative 6, which means put down 6 zeros, and then your number, and decimal place goes after the first 0. So there is our step 3. So this is what I want you to do, right? Find the first and last expected value, and then do your test. In previous semesters, oh, did I do step 1 already?
No.
Ah, shoot. Okay, I totally screwed that up. All right, so step 1. Just squeeze it in there somewhere. Infections is independent of hospital, or infections is dependent on hospital. You could also go call it O sub I equals E sub I, or O sub I is not equal to E sub I. Step 2, write down your alpha. Oh, why I jumped all the way to that? Everybody good with steps 1 and 2? Yeah.
Would the alpha be the same 0.05 for all of them, or just this
Yeah.
example?
Just this if it's not, it's whatever's stated. If nothing's stated, then it defaults to 0.05.
Oh,
I feel like if it's on the test and it's not given, you just have to.
Yep, then use 0.05. Or ask me and say, is it given and I'm just not seeing it? So then step 3, find the first and last expected values, which we just showed you how to do a second ago. Here are all of them. So in previous semesters, people would have to find all of them and then do the observed minus expected squared over expected for all of them and add them up. So the very first semester I taught them, they had to do this and come up with the chi-squared that way. You don't. No, you don't. Instead, you can just do it this way. Matrix, edit A, put in your rows and columns. And like I said, once you change A to be what you want, if you wanted a smaller one, say my A is now a 2 by 7. I just put in 2 by 7 and it automatically make it into a 2 by 7. And I can change that around. And then it'll also overwrite B. So don't worry about what B is. It will make B what it needs to be. So then step 4, make your decision. Since my p-value is really small, way less than alpha, I'm going to, reject H naught, which means in step 5, we have enough evidence to support the claim that infections is related to hospital, or, that's actually probably it. You can't really say O sub I. Yep. All right, let's take a break. 10-minute break.